Okay, so let's start with another multilinear regression example. Now, in this, we will take the housing data set with which contains information about different houses in Boston. There are 506 samples and 13 features variables in this data set. The objective is to predict the value of prices of the house using the given features. So next we will load the housing data from the scikit-learn library and understand it, and we'll also import the required libraries. So let's first import the libraries, that is NumPy, Pandas, sklearn, as you are seeing. Then along with that some sub libraries like train test split, load Boston, this is the data set. Then mean squared error, this again is sub library, and then this DFPD data frame. So first let us load this data set, that is load Boston data set, and then we print the value of the Boston data set to understand what it contains, because it is important that we must know that what is inside the data set. So we can print the Boston data set. So for that we give this command like this, print Boston dataset dot keys. So let's keep on running it also, and before that let's clear it, all the outputs. So once we clear it, then we are going to run each and every cell. Now this cell has been executed. Now this cell also, this is for the importing all the libraries. Then we are going to load the Boston data set, that is for housing. So that's also can be run, so that the data comes, the data is available now. So we print this is of course the remarks, so nothing is going to happen here. Now we are going to print the Boston data set keys. So when we print it, we can see that data, target, feature names, description, and file name. So these are the keys of that, which are again for our information. Now the next is that data contains the information for various houses, target prices of the house, feature names, names of the features, description, of course describes the data set, and to know more about the features, use Boston dataset dot description, that is DESCR. The description for all the features is given below. So you can run this, then we are going to get the description of that. So with that, of course, these are the detailed description of this. Each and every feature is there, Crim, Zin, Knox, all those features are there, and all this. So we need not go into the details of this, but this is that if you want, we can go through all these details of the individual data points or the fields. Then we are going to read this data, that is housing.csv on this, because this is the same data set. So we can run here. So when we run, of course the data comes into data frame, because this data file is already available in our local hard disk. So the prices of the house indicated by the variable MEDV is our target variable, and the remaining are the feature variables based on which we will be predicting the value of the house. We will now load the data into the pandas. So we are now going to run this, and then we are going to check the head, that is top 5 rows. So with that, of course, as we know that we have to df.head gives us this. So 5 records, top records have been printed here, and with all these features, that is Crim, ZN, Indus, Chas, Knox, RM, Age, whatever is there, all that has been printed here. Now after loading the data, it's a good practice to see if there are any missing values in the data. We count the number of missing values for each feature using isNull. That is the way we can check whether the data is intact or not, or there is any problem in that. So let us run that. This of course is a remark, so nothing is going to happen, but now with this we will get to know about whether there is any null data. So that is how df.isNull sum, so all of them are 0, so that means there is no null data. This indicates that, right? Now we are going to go for the exploratory data analysis. Now this exploratory data analysis is a very important step before training the model. In this section, we will use some visualization to understand the relationship of the target variable with other features. Let's first plot the distribution of the target variable MEDV. We will use the distplot function from the Seaborn library. So of course nothing is going to happen in this because it is remark, but now we are going to print a distribution plot. So for that we import the Seaborn and of course matplotlib.pyplot, and then this is the way we can define the range of our in this graph that we are going to have. So we can run this, then we are going to print the distribution plot. So this command is will give you that SNS distplot df MEDV bins are 30 and plot show. So when we run this, you will see that a graph normal distribution plot will be presented to us. Now, as we said, MEDV is the variable that we have taken in for printing this, and this is a normal distribution graph that we can see. There are some outliers which are there which can be seen, because like here and some are at the top, but these are always part of the data set. Now this is the way you can get the normal distribution, or this is known as distribution plot, right? Now we see that the values of MEDV are distributed normally with the few outliers that we have seen. So next we create a correlation matrix that measures the linear relationship between the variables. So the correlation matrix can be formed by using the correlation function from the pandas data frame library. We will use the heat map function from the Seaborn library to plot the correlation matrix. That is the way we can plot the correlation matrix. So this of course nothing is going to happen because it's remark. Now we are going to write the code. Now for doing the correlation matrix, again the correlation underscore matrix df correlation, this is the code, and then round 2. So we are going to have a correlation matrix. Now we are also having the annotation that is true to print the values inside the square. So whatever blocks are going to appear there, we will have the value of that also with this annotation. SNS.heatmap data is equal to correlation matrix, and then annotation is equal to true. So when we run it, you will see that you are going to get a correlation matrix graph like this. This is generated with the help of the that heat map, right? So you can see that all those features which were there, they are all present here, and along with their values, and they are available in the vertical side as well as in the horizontal side. And this is the bar that gives us the guidelines that is how the numbers have been generated, right? So this is the way we can have the correlation matrix. So we have seen the standard distribution, normal distribution, and we have also seen the correlation matrix. Now the correlation coefficient ranges from -1 to 1, that we know. If the value is close to 1, it means that there is a strong positive correlation between the two variables. When it is close to -1, the variables have strong negative correlation, right? So again we can run this, nothing will happen. So our observations are, to fit a linear regression model, we select those features which have a high correlation with our target variable MEDV. By looking at the correlation matrix, we can see that RM has a strong positive correlation with MEDV, whereas LStat has a high negative correlation with MEDV, -0.74. An important point in selecting features for a linear regression model is to check for multi-collinearity. The features RAD, TAX, TAX have a correlation of 0.91. These features pair are strongly correlated to each other. We should not select both these features together for training the model. Check this for an explanation. Some goes for the features DIS and age, which have a correlation of -0.75. Based on the above observation, we will RM and LStat as your features and using a scatter plot. Now we are going to have let's see how these features vary with MEDV. So now we are going to have another plot here, that is scatter plot, and for that we are going to write this code, that is PLT figure. This is the figure size 20,5, features is equal to L stat, RM, and target is MEDV, right? So this part we must always be clear that what is our features that we are considering and what is our target. Then we are going to write, this is a for next loop. So for I is equal to column in enumerate features. Now features are here. So from that, I am taking that as a outer limit. PLT subplot 1 length features, whatever length is there, then you are increasing. So every time you have to increase with this, with the I plus 1, that means we are increasing 1 by 1. X is equal to DF column and Y is equal to target. So PLT scatter, that is the scatter plot that we are going to have. X and Y and marker is equal to O, and plot title is column, plot X label is column again, plot Y label is MEDV. So when we run it, you can see you will get a scatter plot with this. So we can run this here, and now you are getting 2 scatter plots. In fact, one is for this, that means for this L stat, and the other is for RM. So both these plots are available, as you can see here, L stat and RM, and this is the MEDV on both the graphs. So this is how you can get the scatter plot. Now having seen this, we are now moving forward to observations, that is the prices increase in the value of RM increases linearly, and there are a few outliers and the data seems to be capped at 50. So the prices tend to decrease with an increase in L stat, though it doesn't look at the following exactly in a linear line. So this is again, we can execute it, nothing will happen, but preparing the data for training, that is important. So we must go and train the data, and for that we concatenate the L stat and RM columns using NPC provided by the NumPy library. So run this. This is all for our information, our understanding. X is equal to PD data frame, then NPC df L stat and df RM. This again, these are the 2 features that we are considering. Columns are LM stat and RM, and then Y df is equal to MEDV. That is again we have kept the same. So we are running this, and if it has transferred here. Now splitting the data into training and testing. So next what we are going to do, we split the data into training and testing sets. We train the model with 80% of the samples and test the remaining 20%. That is how we have divided. So we do this to assess the model's performance on screen data. To split the data, we use train test split function provided by scikit learn library, and we finally print the sizes of our training and testing the test data to verify the splitting has occurred properly or not. So for that again we run it, nothing is going to happen, but here we are going to train test split. So we are splitting the data. So from sklearn model selection, import xtrain xtest, ytrain ytest, train test split, and random state is equal to 5. That means 5 iterations that we are expecting. This comes with practice, and you can keep changing it also if you want, because you can see that the effect of that. So print xtrain shape. So this will give you that what are the number of rows and columns etc. are there. So print xtrain shape, xtest shape, ytrain shape, and ytest shape. So then we can print this, and you can see that 404, 2, 404, 102, 2, we know that 506 were the total number of variables. So this is how it has been divided. Now this is again 404 and 102. Here second columns are not there, right? So this is the way we have divided our data between the training and testing. Now we are going to go for the training and testing. So we use scikit learn linear regression to train our model on both training and test side. So we can simply run that, and then from sklearn model import linear regression, because now we are going to use this. So we have to import this library. Again, we need not know about what is inside that, but we know that yes, we are going to use it. We need to use it. So sklearn matrix import mean shared error. and then lin model, linear regression, lin model, x train and y train. So that is what we are going to run here, and we will see that it gives us the linear regression. Copy x value, x true, and fit intercept true, and n jobs none, and normalize. This is the kind of output that you get because we have run this. Right? Now we have to evaluate the model. Whatever model has been created, we have to check about for our satisfaction. So we will evaluate our model using RMSE and R2 square. This is the way we can check it. Right? So we can again import all this, that is a scale-learned matrix, import R2 square, because R2 square is again a sub-library available in sklearn. Then y train predict, lin model predict x train. Right? So this is the data which we are going, which we have trained. And now RMSE, root mean square error, NP is equal to square root mean squared error, y train predict. Right? And then R2 square, y train predict. So once we run this, you will see this, of course, for printing purposes, but this is the actual algorithm that we have used for the purpose of training and testing. So once we do that, the model performance for training set, that is what the heading will come, RMSE will come, R2 will come, R2 score will come, and then of course the next line will be there. Y test predict, line model predict x test, RMSE, NP square root mean squared error, y test predict, and R2 is equal to R2 square, y test predict. So this of course one has to go through again and again, so that your doubts or you get the clarity. And then again we are going to print the model performance for testing set. Then RMSE is format RMSE, because we have already calculated it here, RMSE, and then R2 also we are going to have format R2. So all that we are going to run here. So once we run this, then you are going to print this. RMSE is equal to 5.6371 and R2 score is 0.63. So this has come on the basis of all this. And this is, of course, this is the model performance of training set. Here this has given us the first 2 lines, and the model performance testing is given like this. So we can see that both of them, the variation is not much. Here we are having 5.63 and here we are having 5.13. Here we are having R2 square is 0.63, here we are having 0.66. So both of them are quite close. So that is why we can say that our model is correct. Right? So this is the way we can check our performance of the model that we have created. And we will look at ways to increase the model's performance. And if you are not satisfied, you can further improve, maybe by changing the state, that RM state, or maybe by changing the feature itself, or something. Whatever you feel that it will help me in improving the performance, we can do that. So we will look at this, and of course nothing is going to happen. And the conclusion is, thus we can say that the multilinear regression can easily be done with the help of this data set. So this is how the multilinear regression is done for the Boston housing data. Thank you.